All righty. Are we ready, Scott?
I'm ready.
Okay, let's do this. All right. Hello, everyone. I'm very happy to be here. As usual, this is the second lecture on our 2023 guest lecture series for the class Introduction to Computational Design here at the Harvard Graduate School of Design. I am very happy to welcome today Scott Mitchell, one longtime friend, a very, excuse me, I'm having a rough day today. Very big fan of his work. And but before we start, I would like to offer everyone a few reminders. This is a double live meeting. So we have right now a Zoom call going on for participants in the class and GSD affiliates. But this call is also being live streamed right now to YouTube for the general audience. So those of you here in the Zoom call, if you do not wish your image to be broadcasted live, please make sure that you keep your camera off. All right. What we're going to do is we're going to conduct this as a lecture. So what I will do is I will introduce Scott, and then he will give us his lecture. And then after that, I will open it up to Q&A first from people here on the Zoom call. And then after that, we will do it for those of you who are watching this live stream from YouTube. All right. I will be the one for the YouTube folks who will relay the questions from the chat here to Scott. Okay. And without further ado, I would like to welcome Scott Mitchell to the guest lecture series. He is the CEO and founder of Stud.io, a computational construction company, which is the first time that I hear that term. I hope that Scott will perhaps help us unpack why he chose this denomination for his work. He has been, as part of his company, he has been working on very interesting and super cutting edge projects such as the Lucas Museum of Narrative Arts and the MSG Sphere in Vegas. He has been a software engineer previously at Autodesk as part of the AEC Generative Design Group. That is where we actually met each other originally many years ago. And he currently teaches at the Sam Fox School of Design and Visual Arts at Washington University in St. Louis. Without further ado, Scott, the stage is yours.
All right. Thank you, Jose Luis. Let me share my screen real fast. All right. Awesome. Well, thank you for the introduction. Like you said, I am Scott Mitchell. I'm the founder and CEO at Stud.io. And I'm going to talk to you guys about misusing machines and what that means for computational construction.
November is over.
All right. So just first a little bit about what I do at Stud.io and what Stud.io is. So we are a computational construction company. So we take computational design and digital fabrication and take that and work with builders and architects on some of the most complex projects being built today. If you're at the GSD, you may have seen this installation by one of your professors from LADG. Andrew Holder. We did a collaboration with him this past summer and was able to exhibit that on the Harvard campus. So if you saw that, that was a little bit of introduction to what you're about to see today. Our mission is to enable architects to realize their boldest ideas. And what we've come to realize is that means enabling builders to construct those bold ideas efficiently. And the way we are able to do these things efficiently is by combining intelligent software with cost-effective machines. So we're using some unusual machines, and we'll get into what that means and some examples of that. But it's different than some of the machines that you're probably more familiar with. But so our software generates a fabrication-ready model like this through a computational process, and then automatically generates the machine files and the assembly information that you need to go build that exactly as the model has. So we're going to get into a whole bunch of examples, but the idea here is you can see there's a wide variety of different geometries that we're able to take, run through our software, and run through a computational process, and build extremely precisely. And we, like Jose Luis said, we develop software. Stud Finder is kind of our main software. And also the reason we're called Stud.io is because a lot of what we've done is with steel stud framing. But we'll get into a couple other types of fabrication as well. And we've been able to take this software and work with builders and architects to build some pretty exciting projects from the Lucas Museum, MSG Sphere, Nintendo Land, Disneyland, Universal Studios. A lot of really cool opportunities to demonstrate the value of some of the research that we've been doing. But at a glance, what a project looks like for us and what we get brought in for is sort of probably what you guys are studying for computational design. It's you have a bunch of unique but similar conditions, and you want to develop a computational approach that's going to allow that to get designed and allow that to get fabricated and built. So this is an example project. This is an actual project that we worked on where there are all these GFRC, which is glass fiber reinforced concrete columns. They're all slightly different shapes. We want to develop a system that will generate automatically, go to the machines automatically, and be easy to put together. You can see the bulk of this is light gauge steel stud framing that's digitally fabricated. The software is adjusting to changes in the geometry from panel to panel, and basically changes the layout of the studs to accommodate the geometry of that panel. There are also those little rods that just flew off are bent bars, which is another type of fabrication we'll get into. But the idea with all this is that the model is fabrication ready. So you give it the geometry, it gives you back all of the fabrication information you need. Every single screw hole, the length of every single member, all the connections that need to be made, and all that information is contained in the model, can be sent to a machine that's going to make the pieces and then communicated to a person that's going to be putting those pieces together. Almost like a Lego set or an erector set or something like that. So this is the kind of thing that we're doing every day on different projects that are getting built. But I want to back up for a second to sort of the beginning of this story. This is me a little over 6 years ago. This is in Boston at Autodesk over in the Seaport. I was an intern at Autodesk. This was while I was in architecture school, pretty heavily focused on computational design. And they basically gave me this opportunity to come into Autodesk, where they have all these machines in their technology center. And essentially they said, just do something cool with this steel stud roll forming machine. And so I got to spend the summer just focused on that. And basically I haven't stopped since. But, week one, we were doing real simple stuff. The idea in my head was like, I want to find ways to use this machine that no one's ever thought of before. And so probably no one had thought of this before, but it's not necessarily a good idea, but it was a start. So we were playing around in Dynamo and Grasshopper, and we're exporting stuff to this machine. Here we're working with laser cut wood pieces, which it doesn't make a whole lot of sense in hindsight, but led to some other ideas. And by the end of the summer, had actually come up with a pretty impressive structure using this machine. And again, it's building a giant sphere with a steel stud roll form machine, or with steel studs in general. It's just something that people hadn't done before, and that was really what was exciting about it for me. And I could have stopped there, but I wanted to build some generalized system that would allow us to explore basically a whole bunch of other algorithms and things that were of interest to me. And so I started working on this idea that you could take any planar polygon, feed it into the software, and it would generate members and studs on top of it. And I was using Grasshopper. You guys are probably familiar with the exact same workflows that I was using. And I would take every polygon and solve it independently. and ended up having a conversation with this guy who might look familiar to you. And he said, there were a couple of things he said throughout the course of my internship there. He was, I think, a full-time employee at the time, that like Stud.io probably wouldn't be where it is today if he hadn't pushed me in a couple of directions. So just keep that in mind if he ever gives you any sort of direction.
I can't believe you found this. I can't believe you found this photo.
Dude, there's a bunch of them that are pretty good.
Oh boy.
Yeah. But the what's behind him on the whiteboard there is this whole idea of taking a network of lines and say kind of structuring that as a graph, and with all these interconnected nodes, and then working your way across the graph to solve it. I think we were thinking 2D at the time. We've come to do things in 3D, but that's still at the core of the solver that our software is built on. So basically spent the end of that summer / into going back to my last year of architecture school, building out this software, testing it on some different structures, and it built this generalized tool that would take in lines, and it would tell you the valid ways where you could connect studs along those lines. So there's like, for any given line network you give it, there may be none, or there may be a handful of different ways you can orient studs along those lines and connect them in a valid way. So that is the solver that's still at the core of what Stud.io is doing today. And there's a particular type of machine that is sort of a good candidate for this approach, for this type of computational design. So you're probably familiar, these are the types of machines that architecture students and architecture studios are using all the time. They're great for mass customization. We got robots, 3D printers, CNC routers, laser cutters. Like, you can sort of make whatever you want with these machines. But a roll forming machine, which is what you got at the top there, along with a couple other machines that we'll talk about, are not meant for customization. They are meant for mass production. So these are machines that builders and shops have, that are just supposed to just spit out parts that they can take to site and build quickly. So unlike the machines on the left that are built for customization, these are built to do one thing, but just do it efficiently, precisely, and quickly. So what we've realized what we're doing is we're trying to bring the customization that computational design and architecture school kind of teaches you, bring that to these unique machines. And it turns out there's a whole bunch of potential when you do that. And it also turns out it's relatively unexplored. I still think there's a huge amount of potential, just like latent potential for these machines to do extremely cool stuff. But I want to focus in on the roll form machine for a second. So this guy is meant to just roll up studs. So this, if you ever driven by a construction site, you see something like this, like the steel stud roll form machine makes basically exactly this kind of thing. You'll notice it's typically flat. It's typically walls and components are meeting at 90-degree angles, not a lot of geometric variation. And that's because again, it's focused on doing one particular thing. It creates straight studs. It punches, this is the cool capability of it, it can punch holes along the stud, but it can't change the shape of those holes. There's typically like 8, here you see 8 different punches. So that's just a piece of metal that comes down and punches out a piece of metal in the stud as it's kind of rolling up into the correct shape. So again, highly constrained machine that's meant to do one thing. So we're asking ourselves, how can we do interesting things with this highly constrained machine? And we've kind of built a theory and also the software to help us take a very simple constrained operation on the left, develop parametric connections with it, and then even combine those connections into complex versatile systems. And that's an approach it's led to a whole lot of really interesting ideas, interesting algorithms to deploy this idea. And that's what's being used on all of our projects today. So we look at a couple of those connections. connection types is what we call them. This is a very basic one for light gauge roll form systems. So this is like a stud and a track. How you might build a wall. You could also pass one stud through another. Most people are you just do this at 90 degrees, and that gives you most of the typical buildings being built today. But we can change the angle of this. We just have to change where the punches are happening that allow one stud to pass through the other. And if you triangulate this connection with additional connections across the structure, you can fix the structure or two members at a particular angle. And similarly, this is another connection type that we call handshake connection or back-to-back connection. We can take two studs back to back and do this 3 web hole punch, then align some holes on those punches so that if you can put a screw through them, it will fix the 2 studs at a very particular angle relative to one another. Angle can be whatever you want. So it's still pretty simple, just 2 connection types. And most of the stuff I'm showing you today uses just those connection types. But with just those 2 connection types and the parametric nature of them, you can start to do some really interesting stuff. Whereas most people are just building flat rectangular frames, we can start to break out of the plane and do 3-dimensional geometry. Like one of our first tests was just running every platonic solid through this. But you don't have to stop there. We can really feed any surface into what we call the triangle system. And it doesn't matter how complex that is, it can be doubly curved. You can just generate this pattern across it where every single member is unique, but it has all the holes that it needs to connect to its neighbors at the particular orientation that's going to allow the builder to recreate the exact geometry that's in the computer. So that's one example of a system. That was one of our earliest systems. But basically, you can write your own scripts, Grasshopper or Dynamo or whatever language you're trying to use to utilize these tools. You basically just have to draw lines and produce an analytical model that the solver will generate fabricatable members on top of. So you can come up with all different kinds of systems just using this idea of building on highly constrained fundamental components, these operations, into slightly more complex combinations or connections, and ultimately into entire systems. And as someone who has kind of a history with other types of making, this idea I've noticed connects to other things, other ways of creation that I've been involved with in my life, like playing games. But I think the same way you have these components on the left of your pieces in chess, they are constrained in how they can be used, especially on an individual basis. There are very particular rules about how they can move. But what's interesting is when you start to combine those moves into strategies. Similarly with music, you have these very atomic notes on the left that have no variation, but you can combine them in ways according to rules. And as you combine those chords into entire compositions, you can start to play with those rules and play with the ways that you're combining things. So this, I think, is something unique to these types of machines that are industry focused versus the 3D printer, which has no constraints. You have to think creatively about the atomic building blocks of the machine. And I think that's what's really interesting about that is you have to be creative. It's like problem solving. There's like this huge area of potential use of the machine that's just unexplored because people don't think to combine some of these operations in ways that they can be designed or combined. And one of my favorite examples of that is the ability to curve studs coming out of the machine. So the machine it wants to make straight studs. It's marketed on its ability to make straight studs. But it turns out with a certain combination of punches, you can actually start to curve studs in a precise manner coming out of the machine. And basically what you do is you punch what's called an end truss, which is that slit across the web, the wide part of the stud, and 2 little punches on either side of it. And if you snip between the 2 punches, fold them over one another, put a screw through it, it's going to fix the segments of this thing at a particular angle. One of the downsides of that is that you're cutting out some of the the strength of the stud, but if you combine that with another stud that's back to back with it, that has alternating cutouts, you regain that strength, and you can start to take any sort of curve or polycurve and generate studs along that as well. And as you aggregate those curved studs, you can start to generate entire curved and doubly curved geometries this way. And the reason that's so cool is the manufacturer of the machine didn't even have that in mind when they designed the machine. It's just something that happens to be possible given the right creative approach to using the built-in capabilities of the machine. So we're misusing the machine, but producing a extremely valuable use for the machine. And I think that's why we've had some success at Stud.io. Is there are there's a perceived solution space for these industrial machines, which is the typical use cases. So that's what the contractor goes and buys a machine with that in mind. But we think that that's just a small portion of the vast potential of use and ways to leverage what the machines are capable of. And so I think if you go back to those images of me messing around at Autodesk with Jose Luis 6 years ago, that was taking our first steps into what's possible if you start to be really imaginative in how you use the machine. And what's the way it's turned out is like every time you do one little experiment or play around with something, you generate ideas for another experiment that then maybe you go use what you learned there on an actual project, and that project spurs a couple ideas that can be developed further as experiments later on. And I still feel like there's so much, even with just the steel stud roll forming machine, there's so much potential that is still to be explored. And to me, it's like what gets me excited about doing the kind of work that we do. Because it's playful. Like we're playing a game. We are playing the machine like an instrument. So in between projects, which we'll get to in a second, we do fun stuff like try to make furniture out of the machine. We at one point just built a giant bird with the machine, just trying to prove like what sort of detail we could get with basically 2x4 steel studs. We also have a design for a foosball table with the machine. It's like anything you can imagine you can build with this thing that's meant to just build boxes. So I've just got like a whole series of images now that show some of what we've done since that time. So we started playing around with just kind of nonsense details with this machine, but that has led to all kinds of different projects and different geometries and different algorithms that we can deploy on projects. It has also led to the development of our software, which allows people to design the more typical use cases for these machines, but also start to get more creative in what they're designing and what they're trying to build. There's really kind of unleashed creative potential. So anyways, it's been a very exciting journey. And so that's a bit of the history and the theory behind what we've been doing. So I want to talk a bit about a couple of case studies where we've actually used those tools and the knowledge that we've developed on actual projects. So I'm going to start with the Fontainebleau Casino. So this is on the Las Vegas Strip. It opens up in about a month, but I think our scope is pretty much done at this point. We were brought on to help with the porte cochere. So this is this huge entrance to the casino that you drive under, and it's big. But the whole thing we're running through our stud finder software, along with a whole bunch of other Grasshopper scripts to rationalize the geometry. But before we get into sort of the workflow, a little bit about the project. Like I said, it's really big. 500 feet across, 100,000 square feet of finish. There are 436 unique modules that made up the legs that are going out to the ground. Those modules break up into some sort of types, we should say. They're 98 knuckles, and that's where the different beams or legs intersects each other. So the most complex one, we have what we call the legs, which is the actual part that hits the ground, and then the rest are sort of the simple panels, the infill modules. Although even those are all unique shapes. All 436 are a unique shape. So we want to come up with a system that can execute all of those modules. And so as a builder, you might say, like, I just want that to be a box. But as an owner of the casino or as the architect, you want it to have a little bit more geometry, a little bit more, make it a little bit more dynamic. The old way of building that, if you just took each side, built a flat frame, tried to put them together, you're not gonna be able to do that quickly and precisely. So we use, that's that curved stud detail. There's the handshake detail. So with both of those, we can have a sort of a ring of very accurately and efficiently fabricated and assembled studs around the geometry. And then we can connect those with the dimple or the typical connection. And that gives us a system that doesn't just reproduce the two-dimensional faces of the object, but the entire 3D object accurately, no matter what the geometry is. And we don't just stop at generating the model. Obviously, we go to the machines we produce the machine files to make the parts, and we produce the drawings that people have to put these parts together. And I mean, we're basically doing everything we can to make it feel like putting a Lego set together. Even the color coding the drawings versus what's actually showing up on site. So they can basically just like take yellow panel, attach it to red panel. The holes to put the screws in are already there, so they don't have to measure anything or use a protractor. That allows this stuff to go together extremely efficiently. Here's some of those panels installed. But those are the simple panels. So the infill panels take a little bit more complexity to accomplish, but basically the same idea. You just have to deal with where the different extrusions here intersect each other. So just develop a script that's going to handle that and feed the right information into Stud Finder, so that given a module, it will break down into several pieces, which break down into panels. And as that geometry changes, either across the project or as the architect changes the model, all of the assemblies and sub-assemblies and parts update to match the change. And then that goes together pretty dang efficiently, especially for a complex job like this. Like, it's hard to measure that efficiency and that speed sometimes, because it's not like they're building an identical building next door that we can compare against as a control. But we can compare against the client expectations. And for this project, the assembly took a third of what was budgeted. So obviously a lot of value being added for the contractors there. And also that's the kind of cost savings that enables features like this to get built instead of getting value engineered out of projects. There it is, completed. And that one's opening up next month, I think, in December. So moving like half a mile down the strip, another one of our projects was the MSG Sphere. We did not the sphere itself, but we did the collar that's underneath the sphere. Had its own kind of geometric challenges to it that we worked to figure out. So we just, when we enter a project like this, we just think about, okay, what are the constraints on the geometry here? Obviously, this thing is going to be curved and planned. It's going around the base of the sphere. It's sloping in elevation. And the most complex part of this was that it's slanted out, and that slope is changing. So how do we deal with that sort of sloping variable slope as it's moving around the building? And the reason you got to really think through this is because I don't know if you guys have seen the sphere since it opened, but it's like, it's got all these LEDs on the outside. It's a super expensive building, and they needed to cut costs on the collar. And so they wanted to build it out of a flat system. They did not want to build it out of some expensive curved system. So the challenge becomes, how can we take a flat system where we've got a flat frame, the foam on top of it, and create this geometry? So we spend a lot of time sort of as computational designers thinking about geometry, and we start with the basics. So if this is a flat wall, that's obviously very easy to panelize this and break it up into flat panels. If it's sloped out, whatever, it's still easy. If it's curved and planned, you see problem number one, which is that it fans out in elevation. But that one's easy to fix, because if you just, instead of using rectangles, if you make these into trapezoids, you're good. So problem number one solved. Problem number two, though, is, remember we mentioned that the slant is variable. So if we start with the less slant on the left and go to more slant on the right, we start to fan out in section as well, which was not design intent. The owner doesn't like that. So we have to come up with a solution. And intuitively, you think like, I want to just take one corner of each panel and push it to meet its neighbor, so this thing is smooth. But of course, at that point, your panels aren't flat anymore. But at least that gives you kind of an understanding of this twist that is almost necessary for each panel to make it smooth. But we kept going into the geometry, and we realized that really the top and bottom radius of this thing define two arcs or two circles, which define an oblique cone. And what's nice about a cone is it's basically a pyramid with a whole bunch of sides that are flat. So if we instead of our joints, instead of using the architect's joints, if we use joints that run through the apex of the oblique cone, we can get flat panels. So this was kind of the geometry exploration side of this project, and come up with, there are two ways to break this thing up. Either you follow the cone and you can get flat panels, but your joints aren't necessarily what the architect designed, or you use the architectural joints and panels, and you're going to have twisted frames. So we looked at, okay, what would it be like to deploy each of these systems? So on the left, you've got the slanted joints, but flat frames. And on the right, you've got vertical joints, but we have to make up that twist in the finish. And the way that we proposed to do that was, we'll keep everything flat, just change how the frames in the back are oriented. And then the foam that's on the front of this thing, we'll just put all the twist into that foam. So you can cut that with a hot wire, which is the same way they would cut it if it was flat as well. You just have to change how they're moving the hot wire as they cut the foam to get the right shape. And so we gave them both options. They decided to go with the architectural joints, so the vertical joints. That's fine. So we went with the CNC hot wire foam. But this is what the framing system looked like underneath that. So you got just a flat frame that handshakes to a horizontal frame that gives you the correct tilt out. That registered to some other components, and then finally you put your foam on the outside, which gives you the exact geometry you need to line up to the panel right next to it. And one thing that's becoming more and more important to us is not just talking to steel stud roll forming machines, but talking to all the machines that are going to work together to build what we've been calling a system of systems. And there are constraints within each system, and there are constraints between systems. But ultimately, you just need to solve those constraints and send the information out to the machines that are building them. And this works. So we send information out to the roll forming machine, send information out to the drawings that are getting printed, and the humans read and put the parts together. Let me try and speed up through this. We've got the handshake connection there with the alignment holes that fix that bottom frame at the correct angle. We had these brake checks, which are heavier metal that were cut with a laser that also have holes in them that align to holes in the frame. There's a bit of a weld detail that has to happen there. We had CNC cut sheathing that sat on top of this, and then CNC foam that sat on top of the sheathing. And then on site, we had a robotic layout that laser basically turns the exact right location, shoot a laser on the wall, and that's where they would put this embedded angle with a pin in it. And all this is coordinated with the digital model. And then all they need to do is fly this panel in, which has holes that are going to line up to that pin. You just set it right on there. So that's a pretty cool project to work on. I want to move on to another type of machine now. So we've been talking all about roll form machines, but the same idea works for other types of machines. So this is a wire bending machine. If you're not familiar with them, they basically just take a huge spool of wire and bend it to a shape. And when we've walking through the shops where they have these things, like this is typically what they're making. They're making like rebar stuff. They're making shopping carts. They're making the covers for fans, hangers you put on your door, all that kind of stuff. So these are mass production machines. They don't make one of each of these. They make thousands. But we wanted to take this and just make only custom parts for this Mad Architects project in Denver. This is called One River North. Basically just a normal condo building, except it's got this huge canyon carved out of the facade. And so we decided we were going to use the wire bending machine for this. It's a plaster finish. So underneath the plaster would be this bent wire system. All of these digitally fabricated with our software and sent to that machine we were just looking at, and then prefabricated as a set of panels. So basically the steps to make something like this work are, one, you got to familiarize yourself with the machine. And we've talked about kind of understanding the basic operations the machine's capable of. And then we develop software that allows you to just very easily input some geometry and then run it through, generate the operations for the machine, generate the files to run on the machine. And whether as your geometry changes, so those are the files. These are called XYZ files for this machine. You can see each shape has a series of bends at particular angles. But all you got to do is just set up your design surface and set up the bounding box of the panel you want to make, and all the rest of the information is generated automatically. So there are the machine files and then also the drawings the guys use to weld these pieces together. So everything automated, everything within the software. Just in Grasshopper, we set up the surface and the boxes. And again, the idea is to enable architects' design intent to actually happen without compromise. That one's also nearing completion in Denver. Pretty cool project. I think this is the last project I'll show. This is the Lucas Museum in Los Angeles. We've actually done a few scopes on this project, but I'm going to talk about the first one we did, which is the ribbon, the podium ribbon, which goes around the bottom of the building. So for this project, we involved another machine, and this is one that we're using more and more. It's a tube laser. Basically a laser cutter that rolls a tube through it and cuts out different parts of the tube. The idea for using tubes is we needed all these different complex tube assemblies, because we wanted it to be foolproof and members to just come together exactly like the studs did in a foolproof manner. So we have this detail where the laser cutter cuts teeth into the end of tubes, and then you laser cut plates that those teeth will register into. So once the machine's done with the parts, it's just a matter of lining up the teeth with the holes and welding it together. And we start to get into the system of systems idea here as well. So that's how you would generate the tubes for these panels. And there's 193 of these, all unique. We start with those tube assemblies in the back at some complex, unique shape. We have a steel stud system on top of that registers back to the tubes, and then we have bent wires that weld to the stud system, then get cast into the finish. So this is using all of the machines that we've talked about so far, and again, a system of systems. Bunch of different geometries. You throw it at the script that's using our software, and it generates all the fabrication and assembly information for the panels. And here's the images of that happening, just the proof that it all worked. In addition to creating all those, what we call the frame with those machines, with 5-axis CNC routers, we also generated the information for the molds. This is a GFRC project, which is glass fiber reinforced concrete that you have to cast in a mold. So we had the foam mold plus these plywood end boards. We had holes in the mold that lined up to holes in the end board. So you just had to put a pin in that to hold it in the exact right shape. And we had these little triangles on here that what we call the frame locators would register to. So once you put those on, you know exactly where to drop the frame. So you get the exact right product at the end. So each panel is unique, and there's 193 of them. So you basically just have to run each panel through the computational process. It generates the information for the frame. It goes to one fabricator, and the information for the finish and the GFRC, it goes to another fabricator. So the frames were fabricated in one place, sent to the GFRC fabricator, where they lowered it into this mold and cast the GFRC around the panel. And here's that process actually taking place. You can see the frame locators on the left, and the frame dropped into that in the middle, and then getting pulled out on the right. And here's the biggest, I think this was the biggest panel on the job. These things got like 25 feet tall. So just in closing, I think this is a different project, but demonstrates the same idea of on Lucas, where you have one design of a building component that involves a system of systems. And I think we have a unique computational approach that's allowed us to very quickly generate all the fabrication information you need to go build these things. And so, moving into the future, what we're super excited about is all these things that we've shown with steel studs. We want to take it to wire benders, to lasers, and just make it easier and easier for architects to design with confidence, knowing that their designs are buildable in an efficient way. So thank you all very much for allowing me to speak. And the QR code will take you to LinkedIn if you want to connect further.
All right. Thanks a lot, Scott. All right, beautiful. So at this point, I would like to open it up to questions from the audience here on Zoom, and then later on from the audience here on YouTube. But before we do that, before people start thinking about their questions, first of all, thanks a lot. I've seen some of this work previously on some of your talks, and I just do not cease to be amazed by the quality, the depth, and how relevant this is for modern construction, and to actually make these ideas relevant and and constructed. I really resonate with perhaps your earlier statement of, if we want to enable architects to realize their ideas, we do have to be able to enable builders to actually construct these ideas. I think it's actually a very powerful statement, because sometimes we just underestimate, or from academia or from schools, we have this tendency to believe that any form that we create can be somehow made magically, and we tend to underestimate the process and the effort that it takes to bring in random free form into the real world, right? The fact that you're really advancing that field by making it real, I think it's quite commendable.
Well, thank you. Yeah, I feel like I'm fortunate in that that happens to be the thing that's just super interesting to me, is it's not starting with the geometry, but starting with the machine and figuring out what it's capable of. Yeah,
which is it is true. Your work is really a perfect example of perhaps like the bottom-up approach or the idea of, let's take a look at what we have available to ourselves in terms of construction, in terms of machine, and then let's figure out what constellation, what design space can we open by, in your own words, misusing these machines, right? I actually think my 2 cents here. Like you call this misusing, I would call it like super using these machines, because at the end of the day, it's like, yeah, well, maybe this was not the original intent, but you're giving them a value and you're adding such an important layer of possibilities that is software enabled, that it was latent in the machine itself. You just uncovered it because you were designing the right tools that were informed by what you could see in the machine. And I'm actually sure that at some point Howick is going to start adding to their newer machines like different kinds of punch holes, different kind of cuttings, whatever that might be informed by the kind of things that you are opening up. You know?
Oh, absolutely. I mean, that's where we've gotten to that point now where we've been playing in this, I would call it an arena for a while, where we play by the rules of the machine and we do what it's capable of. But I think you do reach a point where you have ideas like, well, what if we change the machine a little bit and change the rules and started playing within rules that we've designed? So that's something that we've been talking about.
Mm-hmm. I've seen in your presentation and even in some of your videos, I've seen that there is somehow, interestingly, a certain degree of effort placed in generating, I'm going to call this old school documentation for some of the parts that you're making. So for example, drawings of the parts, drawings of curvatures, drawings of assemblies, etc., which I find interesting given that your work is so digital, and where the digital aspect of the design, the 3D models, etc., they basically are so connected with the machines that make physical stuff that you could theoretically just bypass this whole tedious process of documentation and just from digital to physical, period, right? But I wonder, what is your experience in this front? Do you still see that contractors need documentation, officials and governments need documentation, people who make this thing, is it still so needed? Why is it so needed? Do you see any of this changing? What are you seeing on the field?
Yeah, I mean, it's a really, really good point. Because, and I don't come from construction. I come from software and I come from design, and I hate drawings. Like, I want everything to be digital. But the reality is we're working with builders who've been doing this for 40 years, for decades. And they have a way that they have done things, and there's value in that, the way that they've done things. And so like all the stuff that we've, tectonic and strategy, like creative process that we've done, like that part's fun. The hard part is how do you show that value to builders? And you have to speak their language. That includes making drawings. You have to reach compromise in, I want to do things my way as what I think is optimal for my system, and what's digital and what's computational. But you have to think about how they're going to see value and how to speak their language. So we have to make drawings. We're slowly convincing people that what if we don't have, like, all of our drawings used to have 1,000 dimensions in them too. So this is a good example. Well, we were able to convince people that you don't need the dimensions because you're not going to need to measure, because the parts are going to come out perfectly. And after enough projects, they realize that that's true. And so we don't have to put dimensions in the drawings anymore.
So what is the value of the drawings then? More in an assembly process?
Yeah, you need some way to say, I got part A and part B, and they go together this way or something like that. We've played around with AR, which is awesome. The setup is a little difficult, especially for me. Like for me, setting up a HoloLens was not easy. For the guys that have been out in the field for decades, it's even harder. So there's still some work that has to be done to move entirely away from communicating assembly information via drawings.
It's interesting that you say you hate drawings, given, if I may, the level of beauty and sleekness of your visualizations. I don't
that's a little, maybe put that too strong. I think things that can't be fully automated, and the more we've automated the drawings, we just don't care anymore. You can just spend time making the automated drawings beautiful.
I know there's many people in the audience right now thinking about how you were making those dynamic 3D visualizations, that they're basically the storytelling of your projects, which seems very, very well thought of and very automated. Is that true? Can you tell us a bit more about how you generate these amazing 3D visualizations?
Yeah, the animations were all produced in Grasshopper. For a long time, they were just produced in vanilla Grasshopper, out of the box Grasshopper. But we've since developed our own plugin that makes it a bit easier. But yeah, so those are definitely automated as well.
Fantastic. Are you going to publish that Grasshopper plugin anytime soon?
I would be happy to. It's we should just make it open source. The reason we haven't is just not quite as polished as the fabrication software.
Mm-hmm. All right. Are there any questions from the audience here on Zoom? All right. I see Andre Almeida from YouTube. He's saying that congratulations, amazing work. He's asking whether if everything was done with Rhino or Grasshopper, or were there other softwares like Fusion, SolidWorks, or anything involved?
Yeah, pretty much every project uses Rhino or Grasshopper, and probably about half of them also use Revit. We just did a project where we did a little bit of Fusion and are working our way towards that. Sort of Revit is our focus right now, because that's where a lot of the builders are. But Fusion and Inventor are ones that we have seen some interest in as well.
All right. It seems like to me that a lot of the work that you've done is offering solutions and to the eternal promises of freeform construction, etc. You have come up with a lot of solutions that are enabling new forms of construction, cheaper, more efficient, more precise, etc. It seems to me that you are somehow holding the holy grail of, we can now build anything. But I'm sure there are some challenges that you're facing. What are the bigger problems yet that you are facing? Yeah. Are there still construction aspects that you haven't tamed? Is it about the industry itself? What is the biggest hurdle you faced these days?
The biggest hurdle we're facing now, so I think, like you said, we're want to enable sort of this idea that whatever you design can get built. And I think the half of that is being able to tell the machines what to do and be able to design the components that are going to the machine. We definitely solved that. But we don't want to just be the only ones doing that. We want to get our software out to more people, and basically just let any designer plug in their design and generate the fabrication information for their design. And that's hard, because I understand the software can go in and hack it to do whatever I want, but making the software usable and versatile is challenging. So right now you sort of have to be the Grasshopper super user to get the full value of the software, and we want to change that. We want most of the people in the industry who are drafting models or producing these things are guys who've just hand modeled things in Revit their whole lives. So we want them to be enabled as well.
Mm-hmm. I see. I can relate to the difficulty. Bien is thanking you for the lecture and wondering if the software that you have designed is applicable to other materials in the future, like wood or other materials, like, for example, for interior installations.
Yeah. In fact, there's a particular machine that we're interested in called a machine maker called Hundigger. It's worth checking out. They produce, it's basically mass customization for mass production for mass timber. And it can be thought of, we think, in pretty much the same way as what we've done with light gauge steel, which is you just give it an analytical model and you should be able to get back fabricatable wood numbers. So that's something we have our eye on, and yeah. In fact, and the other thing I'll add there is at some point, this is a framework for thinking about fabricatable systems. We want to at least open up the API so that you could, what right now a steel stud or a steel tube or a wire or a bar are all different member types that connect with different connection types. We want to open it up so you could actually go write your own C# code with your own member types and your connection types. And so you could be the one to make the wood version of this.
Interesting. From YouTube, we have a question if there's any research interest in irregular materials like bamboo, reclaimed wood, or so.
We haven't really touched on that. I think there might be a challenge there. I don't know. There might be an additional type of solver that would be needed to sort of understand that as a constraint and understand like the irregularity of the members as a constraint. I think it's an interesting idea.
Beautiful. Scott, I think we are at the hour. I don't want to hold most of your day. Thank you very much for being here. It was a pleasure to see you and to see your work as usual. Well, are you open to the last question?
Yeah, for sure.
So Shelley is asking, like, what inspired you to study computer science on top of architecture while in Washington University?
Yeah, so this is a computational design class. I imagine you guys have similar interests to what I had when I was in school. So I started out as just an architecture student and like couldn't bring myself to not use Grasshopper or computational tools on basically every project. And to my own detriment, like my studio projects suffered greatly because of that. But the struggles were necessary to sort of develop a mastery of the computational tools. And at some point, I wanted to dive even deeper into producing my own computational tools, and that led to computer science. I think it was just a deep obsession with sort of doing everything computationally. So you guys are probably on the same path if you're in this class.
Well, I'm trying to preach a little bit of that, a little bit of like, well, when you go beyond other people's tools, you start making your own tools, all this new magic stuff,
I think I have to end with just repeating that, like, Stud.io, there are other people out there that Stud.io wouldn't exist with, but Jose Luis is one of them. And I don't know if he's just like constantly saying amazing things. I guess not. I've talked to you many other times and you've only really said those two things that stand out to me. But like when he has told me anything about computational design and developing software and tools, I just listened to him. And this is when I was a student and paid off. So I would follow the investigations that he suggests for you.
Well, I have to admit I was much brighter 6 years ago. Things only go down after that. But yeah, I appreciate the comment there. And I think with that, we can probably wrap it up. Thanks a lot, Scott. It was a pleasure. And all the best of successes moving forward, developing your work further and making architecture more real, more constructible, and more efficient as well. Thanks a lot.
Thank you for having me.
Bye-bye.
See ya.